Everyone, welcome to lecture 8 of lecture series Signals and System. In the previous video, we saw about the Fourier series and the derivation of the Fourier series coefficient and also the convergence of Fourier series, and finally concluded with Dirichlet conditions and Gibbs phenomenon. In this lecture, we'll see about the properties of continuous time Fourier series, and we'll relate the Fourier series with the LTI system, and finally see the frequency domain analysis. So let's get started. So before moving on to the properties, let me summarize what we saw yesterday. So we saw the synthesis equation. Minus infinity to infinity, ak are the Fourier coefficient, e power jk omega naught t. So this is the synthesis equation. And x of t is periodic with time period t naught and fundamental frequency omega naught. And we also add the analysis equation. ak is nothing but 1 by t naught integral over t naught x of t e power minus j k omega naught t dt. You can see there is an inversion in the sign. And the summation is replaced with the integral and 1 by t naught factor. So this is the analysis equation. So for convenience, let me introduce this notation. This means the Fourier series of x of t gives the Fourier series coefficient ak. Okay, so now let us move on to the properties of Fourier series. So the first property we'll see is the linearity property. So if x1 of t has the coefficients, let's say bk, and x2 of t has the coefficients ck, then ax1 of t plus bx2 of t, and a and b can be complex. The Fourier series of this is nothing but a into bk, right, plus b into ck. So let us see the proof for this. So let's assume some x of t as a x1 of t plus b x2 of t. So you can see from this, x1 of t is given by summation k equal to minus infinity to infinity bk e power jk omega naught t, and x2 of t is nothing but summation k equal to minus infinity to infinity ck e power jk omega naught t. And what is the assumption here? Both x1 of t and x2 of t are periodic with time period t naught. Both x1 of t and x2 of t are periodic with, let's say, the fundamental frequency omega naught. So then only we can add them directly, correct? So now let's add them. A x1 of t, which is nothing but x of t is a x1 of t plus b x2 of t. So this is nothing but a into summation k equal to minus infinity to infinity bk e power j k omega naught t plus b summation k equal to minus infinity to infinity ck e power jk omega naught t. So we can actually take the summation outside common. Then we'll have k equal to minus infinity to infinity a bk plus b ck e power jk omega naught t. This is x of t. So if we say that x of t has Fourier series coefficient ak, then how will x of t be represented as? It will be represented by ak e power jk omega naught t. So by comparing equation 1 and 2, we can say that ak is nothing but a bk plus b ck. So this implies that this is true. So the Fourier series actually is linear. So to find Fourier series of a signal, you can actually break it down into two or more simpler signals and then find their respective Fourier series and add them up in the particular, using the particular coefficient, and you can get the full Fourier series. So next we'll see the time shifting property. Time shift property. So we already know that when we do a time shift, the periodic signal, the period of the periodic signal is not going to change. So period T0 remains same. So as omega naught also. So omega naught also remains the same. So what happens? Let's say x of t gives Fourier series coefficients ak. What about x of t minus t0? Any guesses? Okay, I'll write it down. Then we'll see the derivation. It's e power minus jk omega naught t0 into ak. Okay. So now let's see the proof. So we know ak, right? Ak is nothing but 1 by t0 integral over t0 x of t e power minus jk omega naught t dt. So now let's say x of t minus t0 has Fourier series coefficients as bk. So we need to find bk. bk will be nothing but 1 by t0 integral over t0 x of t minus t0, right? E power minus jk omega naught t dt. Let's say the integral is from 0 to t0 for convenience. Now we can do a change of variable. So let's assume t minus t0 is some variable x, or x is already chosen. So let's assume some tau. Okay. So then what do we have? dt is equal to d tau, and the limits for t equal to 0, tau is equal to minus t0, and t equal to t0, tau is equal to minus t0 plus t0. So still the limits is within one period. It's actually one period. So 1 by t0 integral minus t0 to t0 minus t0. This will be x of tau e power minus jk omega naught. T is nothing but tau plus t0. So tau plus t0 d tau. Okay. So this is again over one period, 1 by t0 integral over one period. And if you see, it is x of tau e power minus jk omega naught tau e power minus jk omega naught t0 d tau. So if you see, this term is not actually falling into the integral. It is a constant. So we can take it outside. So this will be nothing but jk omega naught t0 into 1 by t0 integral over t0 x of tau e power minus jk omega naught tau d tau. So if you observe this term, this is nothing but ak itself, right? We have 1 by t0 x of t e power minus jk omega naught t. So this is ak itself. So bk is nothing but e power minus jk omega naught t0 into ak. So this is what we wanted to prove, right, in the beginning. So what is happening? Whatever minus t0, right shift by t0, is actually appearing as a constant term. And what is happening to the magnitude? Magnitude of bk is same as magnitude of ak. Only the phase of bk is changing, right? So it actually comes as a phase shift in the Fourier series coefficient. The magnitude remains unchanged. So next, let us see what happens when we do a time reversal. So the third property is time reversal. So again in time reversal, does the period change? The period doesn't change, correct? So period T0 does not change. So we can still use omega naught as the fundamental frequency. So what do we have here? X of t is x of t, let's say x of t has the Fourier series coefficient ak, and what happens to x of minus t? So it is actually a minus k, right? So a1 will be, when you time reverse it, it will be a minus 1. Okay, we'll give a proof for this. So what do we have? X of t is nothing but summation k equal to minus infinity to infinity ak e per j k omega naught t, right? And what about x of minus t? This t will just be replaced with minus 1. So ak e per j k omega naught into minus t. So this is nothing but k equal to minus infinity to infinity ak e per minus jk omega naught t. So we'll just use a change of variable k to minus k. Okay. So then our summation will be from infinity to minus infinity. But since it is a summation, the counting doesn't matter. The direction of counting doesn't matter. And I'll get am here, which is minus m, because k is equal to minus m. And I'll get ej minus k I can observe into m omega naught t. But you can see this is the form of the Fourier series coefficient of x of minus t. So if bk is the Fourier series coefficient of x of minus t, then bk is nothing but a minus k, right? If I'm changing the variable again. Okay. So this is the proof. So you can note one small thing here. Consider even signals. We have x of t equal to x of minus t. So for these signals, ak is equal to a minus k, right? So the Fourier series coefficients are also even for even signals. What about odd signals? There we have x of t is equal to minus x of minus t, right? So ak is equal to minus a minus k. So the Fourier series coefficients are also odd. So this can be a quick way to check our answers also in some cases when we know that the given signal is odd and even. And when we arrive at the final answer of finding ak, we can actually substitute k equal to minus k and see if these matches. So next let us look at the time scaling property. So now there is a problem because the period is going to change. So if x of t is periodic with period t or period t0, what happens to x of alpha t? It is going to be periodic as well, but the period is going to change to t0 by alpha. Why? Because x of, let's say x1 of t is equal to x of alpha t, then x1 of t minus t0 by alpha is nothing but x of alpha into t minus t0 by alpha, which is equal to x of alpha t minus t0. So this is again, since x of t is periodic with period t0, this is going to equal to x of alpha t, which is nothing but x1 of t. So x1 of t is periodic with period t0 by alpha. This you have to remember. So what happens to the fundamental frequency? It changes to alpha omega naught, right? So how will our new definition of Fourier series will look like? It will be k equal to minus infinity to infinity. Let's say some bk e power jk alpha omega naught, which is omega naught prime t. So we need to find bk. So we know x of t is nothing but k equal to minus infinity to infinity ak e power jk omega naught t, and ak is nothing but 1 by t naught integral over t naught, right, x of t e power j minus jk omega naught t dt. So what will bk be? Bk is periodic with period t naught by alpha. So it will be alpha by t naught integral over t naught by alpha x of alpha t, right, e power minus jk alpha omega naught t dt. So this t naught by alpha we can also write it as 0 to t naught by alpha. Now we'll do a change of variable, tau equal to alpha t. So d tau will be equal to alpha dt, which implies dt is equal to d tau by alpha, and the limits t naught by alpha will change to t naught itself. So bk is nothing but alpha by t naught integral 0 to t naught x of tau e power minus jk omega naught, alpha and t you can combine to form tau, and dt is d tau by alpha. So now we can cancel this alpha and this alpha. So what do we have? 0 to t naught x of tau e power minus jk omega naught tau d tau. But this looks familiar, right? This is nothing but ak itself. So what do we conclude? The Fourier series coefficient itself does not change, but since the period is changing, we are supposed to change it here. So x of alpha t is nothing but summation k equal to minus infinity to infinity ak e power j k alpha omega naught t. Or you can also write this as k equal to minus infinity to infinity ak e power j k omega naught t is nothing but 2 pi by t naught. So 2 pi by t naught by alpha into t. For x of t, it will just be t naught. Here it is t naught by alpha. Otherwise, the Fourier series coefficient remains same. So Fourier series coefficients remains same. So we can also interpret this as the spectral content is not changing. Only the frequency itself is changing, but the spectral content is remaining same. So next let us see what happens when we multiply two signals. So the fifth property is multiplication. So let's say x of t has Fourier series coefficients ak and y of t as Fourier series coefficients bk. What about x of t into y of t? What are its Fourier series coefficients? Again, one thing to note here is x of t is periodic with period t naught, and y of t is also periodic with period t naught. Hence, their product is also going to be periodic, and with the period same t naught. Okay. So the frequency will not be changing. So x of t into y of t will be nothing but summation k equal to minus infinity to infinity ck e power jk omega naught t. Right? What about x of t? Summation k equal to minus infinity to infinity ak e power jk omega naught t, and y of t is summation k equal to minus infinity to infinity bk e power jk omega naught t. So now let us multiply these two equations. So what will we get? Summation k equal to minus infinity to infinity ak e power jk omega naught t into summation k equal to minus infinity to infinity bk e power jk omega naught t. So one thing you need to note here is you cannot multiply this directly, term by term, right? Because each term in this is multiplied with the entire term here, correct? For example, if I have to write it out, a0 is multiplied with the entire bk e power jk omega naught t plus a1 e power j omega naught t into this same term. Right? And so on, and even on this side it is the same way. But there is a simple way to determine Ck. So let's see about it. So what is the base for Ck? It is e power jk omega naught t, right? So if you see this and this, if I take e power jl omega naught t from here and e power j k minus l omega naught t from here, if these terms are multiplied and I am varying L, when these two terms are multiplied, what will be the base? The base will be e power jk omega naught t, right? So what will be the coefficient of this? It will be al, and here it will be b k minus l. The coefficient here will be al b k minus l, and I am varying L. So I am summing this up. L equal to minus infinity to infinity. So this base is going to be same. Only the coefficients are going to be summed. Right? So this will give me all the terms. This will give me all the terms. Sorry. This will give me all the terms that are having e power jk omega naught t as base after the multiplication. And I'm summing them up all together. For example, if you have to find the terms for e power j omega naught t, what I will do? If I take a0 from here, then I have to multiply it with b1 from here, right? So then only I'll get the term of e power j omega naught t. And if I take a1 from here, I have to multiply it with b0 here, right? Then only I'll get omega naught t, the one factor 1 here. And similarly, if a to b minus 1 and so on. And even here, if it is a minus 1, b2 and so on in the upper direction. So it is like al b k minus l, and I am varying L. So this is like L equal to 0, L equal to 1, L equal to minus 1 and so on. And all these coefficients I have to sum them up, and then I will get the common base ej omega naught t. So this can actually be written as this multiplication. Summation k equal to minus infinity to infinity. Summation L equal to minus infinity to infinity. al bk minus l e power jk omega naught t. But this is our exact expression for Ck, right? So our Ck is nothing but summation L equal to minus infinity to infinity al b k minus l. So x of t into y of t as Fourier series coefficients of this summation. Okay. So next let us see the property of conjugation. So what happens when we conjugate x of t? So x of t, let's say it is ak. So what happens when we conjugate x star of t? Can you say? So let us derive. So x of t is nothing but summation k equal to minus infinity to infinity ak e power jk omega naught t. So x conjugate of t is nothing but, you can take the conjugation inside. AK star e power conjugation of this is minus jk omega naught t. So we already saw how to change this minus to plus. We just have to take a minus k. So k equal to minus infinity to infinity. A minus k star e power jk omega naught t. So what will be the Fourier series coefficient? It is a minus k conjugate. So let us also see what happens when x of t is real. What is the constant? X of t should be equal to x conjugate of t. So then what can I say about the Fourier series coefficients? Ak should be equal to a conjugate minus k. And if x of t is imaginary, we have x of t is equal to minus x conjugate of t, which is nothing but ak is equal to minus a minus k star. So what happens when x of t is real and even? So for real, we know ak is equal to a conjugate of minus k. But for even, we also know ak is equal to a minus k. So we can say ak is equal to ak conjugate. So ak is also real. And since it is also even, ak is also real and even. So what happens when x of t is real and odd? So ak will be equal to a minus k conjugate and ak is equal to minus a minus k. So if we just substitute this here, we'll get ak is equal to minus ak conjugate. So this both implies that ak is imaginary, purely imaginary, right? I'll just mention imaginary and odd. So if it is the other way, x of t is imaginary and even, what do we have? We know ak is equal to minus a minus k conjugate, right? And ak is equal to a minus k, which implies ak is equal to minus ak star, which implies again ak is imaginary and even. So if x of t is imaginary and odd, you know the outcome, because that is the only possibility left. So ak will be equal to minus a minus k star and ak is equal to minus a minus k, which implies ak is equal to ak conjugate. So these both implies that ak is real and odd. Okay, this is a very interesting property. So the next property is something known as the Parseval's relation. Parseval's relation. So I will first state it and then explain about it, and then we'll go for the derivation. It is nothing but the energy of the signal x of t, or the power, right? When it is over a period and 1 by the time period, is the power of the signal x of t is equal to the sum of the coefficients square. And this mod ak square is nothing but, if we know each harmonic is given this way, a power ej k omega naught t. If we take the power of this, power of kth harmonic, it is nothing but 1 by t integral over t naught, and it is ak mod ak e power jk omega naught t whole square dt. Since this modulus is equal to 1, this is mod ak square dt. So this t naught and t naught will cancel. So we will remain with mod ak square. So this mod ak square is nothing but the power of kth harmonic. So the total power of x of t is nothing but sum of the powers of all harmonics. So it is stated like this: the total average power in a periodic signal is equal to the sum of the average powers in all of its harmonic components. So this is the statement and interpretation. Now let us see the derivation. So proof. So we have x of t as summation k equal to minus infinity to infinity ak e power jk omega naught t. We need to obtain mod x of t square, right? So for that we first find x star of t, the complex conjugate of x of t, and this is going to be ak star e power minus jk omega naught t. And if you multiply x of t into x star of t, so we know the multiplication property, right? So we'll get summation k equal to minus infinity to infinity, summation l equal to minus infinity to infinity, al a k minus l star into e power jk omega naught t. But for that these bases should be equal, right? So for that this will be a minus k and this will be plus, okay? Or I'll write it as a separate step. So this is equal to summation k equal to minus infinity to infinity a minus k star e power plus jk omega naught t. So what will happen here? So we want L from here and k minus L from here. If you want k minus L from here, we will get minus k minus L here. So this will be minus of k minus L. And on the left hand side, we have mod x of t whole square. So this is equal to summation L equal to minus infinity to infinity L a into L minus k conjugate e power jk omega naught t. Now we want to find the power, right? Which is nothing but 1 by t, t naught integral over t naught over t naught, let's say. Mod x of t whole square dt. And here integral as well, 1 by t naught. And this same thing comes. Into dt. Now we can take the integral inside and the summation outside. So, and also you can see that these full terms does not depend on t. Only this term depends on t. But since this also depends on k, we have to keep that in mind. So 1 by t naught summation k equal to minus infinity to infinity summation L equal to minus infinity to infinity al minus k conjugate integral t naught e power jk omega naught t dt. So this is equal to t naught for k equal to 0 and 0 for k not equal to 0, right? Because it is the average over one period and not average, it is like the average over one period, and all the sine and cosine terms will go to 0. Only the DC term will remain, and that is equal to t naught. So for only for k equal to 0, meaning here we have to substitute k equal to 0. So this is equal to 1 by t naught. Only k equal to 0 remains. So L equal to minus infinity to infinity al star into t naught. And this t naught cancels. And we have L equal to minus infinity to infinity. This is al mod square. So this is nothing but 1 by t naught integral over t naught x of t mod square dt. So this is what we wanted. Just the change of variable by k will give us this proof, which is called as the Parseval's relation. It is very important and it shows us how the time domain signal is related to the spectral components, right? Okay. So next let us look at the property of differentiation. 8. Differentiation. So if x of t is a Fourier series is given by ak, what happens to dx of t by dt? So let's find out. Let me show the proof. So we have x of t is nothing but summation k equal to minus infinity to infinity ak e power jk omega naught t. So if we take the derivative on both sides, you can see all ak and all are constants. So only this term will be in the derivative. And this is nothing but summation k equal to minus infinity to infinity ak jk omega naught into e power jk omega naught t. So this is going to be remaining same. So still x of t is periodic with period t naught, and the Fourier series coefficient has changed to jk omega naught into ak. Okay. And the next property will be integration. So these are simple. So you can also see that from here, if we call this as bk, and x of t is nothing but integral of this signal. So this is going to be bk by jk omega naught, right? Anyway, let's go ahead and derive this. So x of t gives ak, what about minus infinity to t x of t dt. This is the integral question mark. So this is actually, we said it to be ak by jk omega naught, right? So let us see if it's the case. Okay. So we have x of t is nothing but summation k equal to minus infinity to infinity ak e power jk omega naught t and integral minus infinity to t x of t dt is nothing but integral, you can take it inside, integral minus infinity to t e power jk omega naught t dt. So this integral is nothing but e power jk omega naught t by jk omega naught from minus infinity to t. So when it is equal to t, it is the same, and when it is equal to minus infinity, this is going to go to 0. Okay, so this will be e power jk omega naught t by jk omega naught, and then we have this integral is equal to summation k equal to minus infinity to infinity ak by jk omega naught into e power jk omega naught t, which is what we wanted. So next there is something called as periodic convolution. It is especially defined for periodic signals. Since for periodic signal their extent itself is infinite, so their convolution, direct convolution may not converge. So let's say x star of t, y of t equal to, we know it is minus infinity to infinity, x of tau, y of t minus tau, d tau. This is the convolution. So let's define something called as periodic convolution. So let's call it this way. We put a circle. So it is defined only over one period. Let's say t naught. X of t and y of t is periodic with t naught. And then x of tau, y of t minus tau, d tau. It is just defined over one period, which can be 0 to t naught or anything. Because x of t and y of t are periodic with t naught, the limits can be changed. It can be minus t naught to t naught by 2, like minus t naught by 2 to t naught by 2, or 0 to t naught by t naught, and so on. So now let's see what happens to this in terms of Fourier series coefficients. So x of t has Fourier series coefficients ak, and y of t has Fourier series coefficients bk. And what about the periodic convolution? So this actually has a Fourier series coefficient of t naught into ak into bk. Okay. So convolution actually translates into multiplication with some additional factor, which is the period. Right? So let us prove this. Proof. So we have x of t equal to summation k equal to minus infinity to infinity ak e power jk omega naught t. Y of t is equal to summation k equal to minus infinity to infinity bk e power jk omega naught t. So x of t periodically convolved with y of t is nothing but integral over t naught. Let me take 0 to t naught. X of tau, right? X of tau, y of t minus tau d tau. And this is nothing but integral 0 to t naught, summation k equal to minus infinity to infinity ak e power jk omega naught t into summation k equal to minus infinity to infinity bk e power jk omega naught into, this is tau, right? T minus tau d tau. So now we can consider this as minus infinity ak e power jk omega naught tau. And this one we can consider this e jk omega naught t is like some phase. So we can take it as part of bk itself. Bk e power jk omega naught t together d power minus jk omega naught tau d tau. Okay. And we know this multiplication how it will turn out, right? So this is minus here. So if we just do a change of variable from k to minus k, this will turn out to be jk omega naught tau. This remains same. And this will be b minus k e power minus jk omega naught t, right? Into e power jk omega naught tau into d tau. So this multiplication we know. We can actually rewrite this as k equal to minus infinity to infinity summation L equal to minus infinity to infinity AL into B L minus K, right? Because it is K minus L actually, but since there is a minus sign, it will be L minus K e power minus J into K minus L. We can also write it as J into L minus K omega naught T, right? And this entire term comes here, and we have e power jk omega naught t. So this is the integral, and the k terms come here, and d tau. This is tau, right? So now we know again that if we take the integral, only tau is coming here. So this will again be equal to t naught for k equal to 0 and 0 for k not equal to 0. So in this summation, we can just substitute k equal to 0 directly, because that is the only term that is going to remain. So BL e power JL omega naught t. So this is nothing but the convolution, periodic convolution. So now if you just replace L with K, and I forgot the factor T naught here. So T naught AL AK BK e power JK omega naught T. So you can see actually that this is the Fourier series coefficients. So that is what we already got. Okay. So now let us go ahead and see the relation between the Fourier series and LTI systems. Fourier series and LTI systems. So we already saw when we pass e power st, the complex exponential through an LTI system, it turned out to be an eigenfunction of the LTI system, and we got some h of s into e power st. Right? Now we are actually able to represent periodic signal in terms of Fourier series, which is ak e power jk omega naught t. So if we just replace s with jk omega naught, what do we have? E power jk omega naught t passing through an LTI system gives us h of jk omega naught into e power jk omega naught t. So since this is a linear system, even if we pass some ak e power jk omega naught t, then we'll get ak here, h of jk omega naught e power jk omega naught t. And if you also sum this up, we'll also get the summation term here because of the factor that it is linear. And this is nothing but the input, and this is the respective output. So the output of LTI system y of t is nothing but summation k equal to minus infinity to infinity ak h of jk omega naught e power jk omega naught into t. So what is this h of jk omega naught? We already know h of s, right? So h of s is nothing but it is related to the impulse response h of t. So it is h of tau e power minus s tau d tau. Right? From the convolution we got this. So h of jk omega naught is nothing but replacing s with jk omega naught minus infinity to infinity h of tau e power minus jk omega naught tau d tau. And this is called as the frequency response of the LTI system. So you can observe that it is actually similar to finding the Fourier series coefficients of h of tau, right, except for 1 by t naught factor, which means that this is actually describing the spectral components of h of tau, hence the name frequency response of the LTI system. So let us go ahead and analyze this further. So frequency domain, analysis. So we have the output y of t as summation k equal to minus infinity to infinity ak h of jk omega naught e power jk omega naught t. Suppose let's say I want to do some filtering actions. Let's say low pass. So this is a periodic signal. So they will have a spectral component, right? So AKs are there as K. Let's say I want to limit only to the first and second. So limit to only first two harmonics. Then what do I have to do? So this AK I can't modify because it comes from the input, and this also I can't modify because it is acting as a basis. So I need to modify this. If I take h of jk omega naught as 0 for k greater than 2, then only the DC plus the first two harmonics will be present, correct? Then y of t will be nothing but A0 h of 0 plus A1 h of j omega naught plus a minus 1 h of minus j omega naught plus a2 h of 2j omega naught plus a minus 2 h of minus 2j omega naught. So we can see only the first two harmonics plus the DC term is available for us. So if we are able to modify this h of j omega, jk omega naught, then we can obtain our desired function of modification in the frequency domain. So in many cases this is useful. Even if we want to eliminate noise present somewhere at a higher frequency, then we can do such a filtering to eliminate such a noise. So there are also cases in which I want to remove the low frequency signals and keep high frequency signals, right? So then I need to have something like a high pass filter. Correct? So I can have h of jk omega naught, this is k, such that it is 0 for lower components and actually has some value for higher components, right? Here it is the opposite. It is having value for lower components, not versus k. It is having value for lower components and is 0 for higher components. And let's say we don't want to modify the frequency part, but we want to modify the phase. Then what do we do? So we again have this. So since this is a complex number, h of jk omega naught, we can write it as having a magnitude and a phase. So the phase will actually be e power j phase of h of jk omega naught, right? So if I want to modify only the phase, then I can set this to 1, in which case y of t will be summation k equal to minus infinity to infinity ak e power jk omega naught t plus j into this phase term. Okay. So we can see that this frequency response actually gives us a different perspective to play with the system properties. It enabled us to see a new way of seeing the signal in terms of the components of its frequency, or called as the spectral components. So that is the power of Fourier series. So this brings us to the end of the discussion on Fourier series. In the next lecture, we'll be actually solving some problems based on this topic. So I would urge you all to go through this topic once again from the book so that you get a better and deeper understanding. Thank you. Stay tuned. Take care. Bye-bye.